was taken.
Backyard.
National Park?
Mars National
Mars.
Yeah.
It was taken by the Curiosity rover. It's called Endeavour Crater. So we're waiting for another committee member to arrive. And then start. He's coming from Omaha. Please.
So thanks everybody for coming to Mamur's defense. What we'll do is have him present for somewhere between 20 and 120 minutes. And during that time, we'd ask that you keep your questions, maybe make a note to yourself or something. For the committee members, if we have particular questions that we need to ask right away so that we understand following slides, we'll go ahead and just jump in and do that. But largely, we'll try to keep all the questions for the end. We'll allow a Q&A period after he's done talking so that you all can ask your questions. Then we'll kick everybody out except him, and we'll grill him really, really hard for a few minutes. Then we'll kick him out, and we'll grill each other for a few minutes, and then we'll know the outcome. So thanks again for being here, and Mamur, take it away.
Thanks, Dr. Nelson. Jose, can you turn off the light, the back one? Yeah. All right. That's good. Okay. Thank you, everybody, for attending today. So I've been working on these projects for about the last 3.5 years or something, and yeah, I'm going to present all those 3.5 years of work in this 45 minutes or so. So this project was funded by NASA Nebraska Space Grant and NASA EPSCoR, and NASA actually wants to send robots in the extraterrestrial planets because in other planets the environment is very inclement for humans to survive. So it's better if they send the robots there first, and then the robots perform experiments, and gradually they probably not only perform experiments but also build habitats there for future human exploration or even colonization. So the only problem here is it's very expensive to send robots or any payload into space. So say this bottle, if its weight is 1 pound, then how many dollars minimum it might take to take it to low Earth orbit?
50,000.
Fortunately, it's reduced a lot.
It has reduced.
Right now, it's $1,800 is the minimum cost per pound. I think it's SpaceX Falcon 9 rocket that can take it, but only for 1 pound, $1,800. That's a lot. So we don't want actually to send every single robot for every single purpose. Rather, we want maybe some robots which can perform multitasking. So in this case, actually, modular robots are best candidates. Like modular robots, they can perform self-reconfiguration, and so they can actually perform multiple tasks in different configurations. So that's an introduction about modular robots. So exploration. Okay, we've been exploring since a long time, and we still are explorers. And why we need to do exploration and expedition? It's because we are using up the limited resources. But here's the paradox. Resources are not actually limited. It's our technology which is limited, because of which we cannot go and reach to the stars and bring back all the resources that we have in this big universe. Now, our early explorers, they have explored a lot in this planet, and that's why we are here. Let's think about Nebraska. It's very cold in several months, right? And here's an example, a case study you can say. I come from a country where the lowest temperature I ever found was 46 degrees Fahrenheit. And that's considered kind of warm in Nebraska. So if I can come here and then say, I can find that the weather is actually, like there is air conditioning system and everything for taking the temperature up. And you can use lots of jackets and clothing, which is pretty much identical to going to other planet and then using controlled weather for the habitats and just wearing the spacesuit. So our exploration has actually reached farther. So far, we just started space exploration, and we have 12 people who so far walked on the moon. That's about like half a century ago, all of them, pretty much. And we had 4 robotic rovers that rolled on Mars. And there are 2 of them, they are still in the Mars and they're active. One is the Opportunity rover, and another one is the Curiosity rover. So Curiosity rover is very keen at taking its selfies. That's why we have this picture. And we have one spacecraft which already left the solar system. That's Voyager 1. So it went so far that even Sun doesn't have any gravitational pull, significant gravitational pull on it. And we have a football field-sized space station which is orbiting the Earth. So those are great achievements. We have identified some of the planets and other moons of different planets in the solar system where we can actually possibly go and build human habitats in the future. But in the beginning, we need to do the robotic exploration. So Moon, there were already robotic explorations, and then human beings, they went there already, 12 people walked there. And Mars, there are rovers rolling there and performing experiments. Venus, it was explored a lot by the Soviets in the 1970s. And this is a picture by the Roscosmos. And Titan is one of the moons of Saturn. So that was a picture taken by European Space Agency. They sent Huygens probe, which took the picture. That's the farthest we went and did the soft landing so far. And there are a couple other places like Europa, the moon of Jupiter, and Enceladus, which is the moon of Saturn again. So if you closely look at the terrain types, is it very similar to this table? No, it's very unstructured and rough terrain. And that's a big challenge for the robotic rovers or whatever type of robot you send there to maneuver on those surfaces. Now, so far the rovers, robotic rovers we sent in different planets. This is the image generated by NASA. So the farthest we went was the Lunokhod, that's the Soviet rover on Moon. That went like about 42 kilometers. And Opportunity is still active, and it's almost there. It's almost there pretty much, getting the same distance. And the other one which is active is the Curiosity rover, which went so far 4.6 kilometers. Now, if you see that Opportunity over there, it went a long way, and Spirit, it didn't go that far, but those were actually all in the same mission, both of them. And that's the place where you can understand that this is a matter of uncertainty in those environments. Some of the rovers might succeed, some of them might not. And the common features of these are wheeled rovers, and they performed locomotion, took pictures, and they did some light duty works like taking rock samples and then performing some testing on them. those were the common tasks of the rovers. Now, there is one problem about the wheeled rovers or even the legged ones. And recently, this is NASA Athlete, which is a combination between the wheeled and legged configuration. So the problem here is the wheels and the legs, they have some finite size, right? So if they are in front of some obstacles, which are probably much larger than the wheels or the legs, then they cannot actually traverse that obstacle. So this is a problem about scalability, which is possible to solve using modular robots. This is an example of kubelets, modular robots, and these are each single modules of the robot, and they have the docking mechanisms, they have some level of autonomy, and they can connect with each other to form larger teams, or assemble to make robots that are probably bigger. And that's the way they can actually perform scalability, and then they can become large robots to scale over the obstacles. Now there are some other characteristics of modular robots. The picture on the top is